In the previous class, I have discussed the solutions for the questions in the assignment in center of mass and conservation linear momentum up to question number 45. So now next I am going to continue the discussion of the solutions for the questions in the assignment in center of mass and conservation linear momentum starting from question number 46. Look at the question number 46 on the screen. I will once read it out. Masses 8, 2, 4, 2 kg are placed at the corners capital A, capital B, capital C, capital D respectively of a square ABCD of diagonal 80 centimeters. The distance of center of mass from A will be. So we can draw a figure. So here 4 masses 8 kg, 2 kg, 4 kg and 2 kg are placed at the corners A, B, C, D, which are denoted by M1, M2, M3, M4. You are asked to find distance of center of mass of system of the 4 masses from the corner A. Because you are asked to find the distance of center of mass from the corner A, we can for convenience in calculation, we can choose the corner A as the origin of the coordinate system. We can choose the corner A as the origin of the coordinate system. So the mass M1 of the first mass placed at the corner A is 8 kg. Mass M2 is 2 kg. Mass M3 you can take 4 kg. Mass M3, M4 equal to 2 kg. And for coming to the coordinates, for the first mass placed at the origin, you can take x coordinate is 0. Even y coordinate is 0. For second mass which lies at B, we can choose x-axis along the side AB and y-axis along the side AD of the square. So x coordinate for second mass placed at B is equal to length of side of the square. The y coordinate is 0 because it lies on x-axis. For the third mass M3 placed at the corner C, the x coordinate is A. Y coordinate is also equal to A. For the fourth mass placed at the corner D, x coordinate can be taken as 0 because it lies on y axis. The y coordinate equal to A. You are not given the length A of the side of square, you are given the length of the diagonal square. So the length of the diagonal square, as you must be knowing from the school level geometry, root 2 times the length of one of the sides. The length of the diagonal square is equal to root 2 times the length of one of the sides. That means A into root 2 is equal to 80 centimeters. From that you can know the value of A here. So x coordinate of the center of mass, system of the 4 masses, we can write M1 x1 plus M2 x2 plus M3 x3 plus M4 x4 divided by M1 plus M2 plus M3 plus M4. So here M1 equal to mass M1 at the first corner is 8 kg, x1 is 0. M2 is 2 kg, x2 equal to A. M3 is 4 kg, x3 is also equal to A. M4, fourth mass equal to 2 kg and x4 equal to 0. By M1 plus M2 plus M3 plus M4. This you can simplify it. X coordinate of center of mass equal to 6a by 16 or 3a by 8. Similarly, you can find the y coordinate of center of mass in terms of A, and substitute the value of A in the last step. Y coordinate of center of mass, the similar way, you can write M1 Y1 plus M2 Y2 plus M3 Y3 plus M4 Y4 divided by M1 plus M2 plus M3 plus M4. Come on, all of you. Substitute these values. Can substitute M1 equal to 8 kg, M2 equal to 2 kg, M3 equal to 4 kg, M4 equal to 2 kg. Y1 equal to 0, Y2 equal to 0, Y3 equal to A, and Y4 equal to A. Can substitute the values of M1, M2, M3, M4, Y1, Y2, Y3, Y4. Come on, substitute and simplify it yourself. If you want, you can take a pause and complete the simplification. So you are supposed to get the y coordinate center of mass also equal to 3a by 8. So distance of center of mass from the origin. The origin is at the corner A. The distance of center of mass from the origin is at the corner A. There will be under root of xcm square plus ycm square. Come on, substitute xcm equal to 3a by 8 and ycm equal to 3a by 8. Come on, do the simplification part yourself. In case you need time to copy the solution, you can take a pause and copy the solution and complete the calculation. So you get 3a by 8 times root 2. A root 2 gives you a length of the diagonal. We can need not substitute the value of A, can directly substitute A root 2 equal to 80 centimeters here. So that will be 3 by 8 into 80 centimeter. So you get the answer of 30 centimeter. If you want to copy the solution, you can take a pause and copy the solution of the problem. So for question number 46, second option is answer. Look at the next question, question number 47. Two bodies of masses 2 kg and 4 kg are moving with velocities of magnitudes must be there 2 meters per second, 10 meters per second towards each other due to mutual gravitational attraction. Then the magnitude, better write magnitude there or assume that there is magnitude. The magnitude of velocity of center of mass will be. So velocity of the center of mass, system of the two masses given by Vcm bar equal to M1 V1 bar plus M2 V2 bar by M1 plus M2. Here M1 equal to 2 kg, M2 equal to 4 kg. The two masses are moving towards each other. That means the two velocity vectors V1 bar and V2 bar are directed in opposite directions. So let us choose the direction of V1 bar in the positive direction of x-axis. That means V1 bar in vector form, you can write 2 meter per second into I cap, or 2 I cap meter per second. I cap is the unit vector along positive x-axis. As you must be knowing, as I discussed in vectors, any vector can be written as product of its magnitude and unit vector same direction. V2 bar is the velocity vector directed towards left side in the negative direction of x-axis. That you can write 10 into minus I cap meter per second. So now I can substitute M1 equal to 2 kg, V1 bar equal to I cap, M2 equal to 4 kg, and V2 bar equal to minus 10 I cap meter per second. M1 plus M2 will be 2 plus 4 kg. Units of mass get cancelled. This you can try to simplify it yourself. This will be 4 I cap minus 40 I cap by 6 meter per second. So minus 36 by 6 or minus 6 I cap meter per second. The negative sign indicates that the velocity of center of mass is directed towards left, the negative direction of x-axis. So the magnitude of the velocity of the center of mass of system of the two bodies will be equal to 6 meter per second. So that's the answer for the given question. So for question number 47, second option is the answer. Next, see the question number 48. Three identical spheres, each of mass 3 kg, are placed touching each other with their centers lying on straight line. The centers of the spheres are marked as P, Q, R respectively. The distance of center of mass of system from P is. So here you are asked to find distance center of mass of system from the center of the first sphere, denote marked as P. So distance between So to find the distance of center of mass of system of the three spheres from center P of the first sphere, we can choose the center P of the first sphere as the origin of the coordinate system. To find the distance of center of mass of system of the three spheres from center of the first sphere, we can choose the center of the first sphere as the origin of the coordinate system. So that x1 you can take, we can choose the line joining the centers of all the spheres as x-axis and center of first sphere as origin. So x coordinate first mass m1 of sphere. First sphere you can take it as 0. Q is the center of second sphere of mass m2. R is the center of third sphere of mass m3. x2 is the distance of center of the second sphere from origin. We are choosing the coordinate center P as origin here. x3 is the distance of center of third sphere from origin. So in case A is the radius of each sphere, because the three spheres are identical, then you can write x2 equal to, from here to here it is A, another A, that is x2 equal to A plus A or 2A, and x3 equal from here to here it is A, that is radius of first sphere plus diameter of second sphere, that is 2A, plus radius of third sphere gives you x3. So x square as center of mass of system of the three spheres can be written as m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3, because all the three masses are equal. This you can write x1 plus x2 plus x3 by 3. As I discussed in the past, that if all the masses are equal, the x coordinate center of mass will be arithmetic mean at the x coordinates of the individual masses. So here x1 is 0, x2 is equal to distance from P to Q, x3 is distance from P to R. Therefore, x can be written as PQ plus PR by 3. So that's the answer for the given question. X coordinate center of mass. But in case you are given the radius of each sphere, this can be written as PQ can be written as x2, or PQ can be written as 2a, PR can be written as 5a, that you get 7a by 3, where a is the radius of one of spheres. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. The second one. So for question number 48, second option is answer. Next, you look at the next question, question number 49. A hole of radius small r by 2 is cut in a disk of radius small r having mass m. The center of mass of system will be. This case I have discussed one of the special cases. In general, in one of the special cases which I have discussed earlier, if a small circular piece of radius small r is removed from one edge of a uniform circular plate of radius Kepler, then distance of center of mass of the remaining plate from center of the original plate will be small r square by Kepler plus small r. Here, instead of Kepler, you are given small r for radius of the original plate, original disk. In place of small r, here small r in the discussion I have done in the past, in the special case, is used to denote the radius of circular piece which is removed. So that is given as r by 2. So in place of small r, you can write r by 2 here. So that comes out to be r by 2 into r by 2 divided by 3 r by 2. That comes out to r by 6. That means distance of center of mass of the remaining plate from center of the original plate will be r by 6. I mean, you can solve this way in case you remember the conclusion which I have discussed in one of the special cases in the theory part. But sometimes you may not remember this conclusion. Still, you should be able to solve the problem. Therefore, I would like to also solve this problem by the alternate way. That means by the method you can solve it in case you don't remember this conclusion. That means whatever method we followed earlier for arriving at this conclusion in the special case, in one of special cases, same method we have to repeat. But I would like to discuss the other method also. That means the usual method we are supposed to follow for subject to questions. So coming to the alternate method, let M1 be the mass of the remaining circular disk, and let M2 the mass of circular piece which is removed. If the circular piece which is removed from one edge is again put back in the original position, the center of mass of system of M1 and M2 will be at C. That means at the center of the original plate. C lies in between C1 and C2. C2 means center of mass of M2. C1 means center of mass of M1. Here M1 is the mass of the remaining plate. M2 is the mass of circular piece which is cut out. So let D1 denote distance between C1 and C. Let D2 denote distance between C and C2. As we discussed earlier, for system of two mass M1 and M2, ratio of the distances of their center of mass, ratio of the distance of two particles from their center of mass will be called inverse ratio of their masses. And ratio of masses M2 and M1 is equal to ratio of the areas. Because the uniform plate having same thickness and density throughout. Mass can be done volume into density. Volume is equal to area into thickness. Thickness is denoted by T. Rho with the density. It is uniform plate, so thickness and density are same throughout. Area of the circular piece removed is equal to pi into square of the radius of circular piece. That is equal to r by pi into r by 2 whole square. Here is the area of the remaining plate. Area of the remaining plate is equal to original area of the circular disc before it is that hole is made minus area of the small circular piece which is removed from one edge. So this has to be simplified by yourself. So you get d1 by d2. So you can cancel pi here. So r square gets cancelled here. 1 by 4 divided by 3 by 4 or 1 by 3 you get. So d1 by d2 you get 1 by 3. So d2 you will get 3 times d1. From the figure you can observe, or d1 you can write d2 by 3. d2 is equal to radius of circular hole, which is equal to r by 2 by 3, r by 6. So distance of center of mass of remaining plate from center of original plate is r by 6. If you want to copy this alternate method also, you can take a pause and copy the alternate method. So for question number 49, fourth option is answer. That means center of mass of system of the remaining disk will be at a distance r by 6 from center away from the hole along the common diameter. So fourth option is answer. So look at the question number 50. 3 identical bricks of length L are placed on the top of each other as shown in the figure, so that part of each overhangs the one below. Find in terms of L the maximum value of the total overhang X. Now see here, if you consider first the top block, for the top block not to fall, below the second block, middle block, the center of mass of the top block should lie within the edge of the second block, because the weight mg of the first block at the top can be due to acting at its center of mass denoted by C1 here. So this top block will fall down below the middle block if in case the center of mass C1 of the top block is to the left side of this edge. So for not to fall, I mean for the top block to not to fall below the middle block, C1 should be to the right side of this edge of the middle block. So at the maximum, the length of the top block that can project beyond the left edge of the middle block is L by 2. Now center of mass of the middle block will be at the geometric center of the middle block. So at a distance L by 2. Therefore, in the situation we are discussing, the center of mass of C1 and C2 will be at a horizontal distance equal to half of L by 2 or L by 4. So the center of mass of C1 and C2 will be at a horizontal distance equal to L by 4. That means the two blocks, the top two blocks of mass, each of same mass m, because they are identical. Can be one block of mass 2m at this position, at center of mass system of the two blocks, which will be at a distance L by 4 from this edge. Therefore, the maximum value of x for which the block can stay in equilibrium is that the center of mass of system of the top two blocks should lie within the left edge, to the right side of the left edge of the third block at the bottom, that is bottommost block. The center of mass of system of the first and second blocks from top, that means top two blocks, should not lie to the left side of this bottommost block. So the center of mass of these two blocks should be at the most can lie here. Actually, it should be to the right side of this point. So at the maximum it can lie here. So therefore the maximum value of x can be taken as L by 2 plus L by 4. That will be 3L by 4. So for question number 50, third option is the answer. See the next question, question number 51. A rod of length L is non-uniform. Linear density, mass per unit length, varies linearly with distance from left end. Then its center of mass from the left end is at a distance. The linear density at the left end may be taken as 0. So we can choose origin at the center of the left end of the rod and x-axis along the axis of the rod. So by symmetry of the situation, you can say that the center of mass of the rod lies on x-axis, that is on the axis of symmetry of the rod. So at the left end, linear density is 0. So linear density means mass per unit length of the rod proportional to distance x from the left end. So you can put a constant of proportionality. You can write mu equal to some constant. You can denote it by c, suppose, or k into x. Let us consider small element of the rod with infinitesimally small thickness dx. We'll consider small element of the rod whose center, the element is in the form of thin circular disc, whose center is a distance x from the left end, and thickness of this elementary disc is dx. So the rod can be imagined to be made up of large number of small elementary discs, each of infinitesimally small thickness dx. So we consider one of such elementary discs with infinitesimally small thickness dx, with its center at distance x from the left end of the rod. So you may assume that mass linear density to be almost same at all points within this thickness dx. So mass of that elementary part of the rod or elementary disk can be written as mass per unit length into length of that elementary part, nu into dx. Nu is the linear density, mass linear density, means mass per unit length, which you can write K into x. So for the elementary disk at the left hand, you can take it as x as 0. For the elementary disk at the right hand, x is L. So x coordinate of center of mass, as I discussed, the method to find the center of mass of continuous bodies. Integral x dm for all the elementary disks between x equal to 0 and x equal to L divided by integral dm from x equal to 0 to x equal to L. So integral dm from x equal to 0 to x equal to L gives the total mass of the rod. So you can write here dm equal to, from here, kx dx. The denominator also dm can be done as kx dx. So this you can write. K is a constant, can be put outside the integral symbol. So integral of x squared dx 0 to L divided by k into integral x dx 0 to L. K can be cancelled. Integral x squared dx, you can write x cubed by 3 divided by x squared by 2. This is 0 to L. Here also limits are 0 to L. So if you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. Can apply the limits here, upper limit. You get L cube by L square. L cube minus 0 by L square minus 0. So you get 2L by 3 as the answer. So distance of center of mass from the left hand will be 2L by 3. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 51, fourth option is the answer. See the question number 52. This similar question I have discussed in the past. So look at the question number 52. This problem, you can observe that similar to the question number 34. I am going to discuss this in brief because I have already discussed similar question in the past. That is the question number 34. If you want, you can again go through the solution of question number 34. Probably you have copied the solution of question number 34. So you again go through that solution of question number 34, then again come to this problem. Then it will be easier for you to understand the solution of this problem. Once I read out the question and show you the diagram related to the question. The following diagram is the small prism of mass capital M slides down on the bigger prism of mass 5m from the position shown at the top of the bigger prism to the position at the bottom of the bigger prism as shown in figure. By what distance does the combination move to the left if the bigger prism initially rests on a frictionless floor? That means you have to find the distance through which the bigger prism moves to the left side. See the figure here. You can observe from the figure. I take the mass of the smaller prism by m1. Please go through the solution of question number 34 again. We cannot, as it is, discuss the entire discussion again. So you can take mass m2 of the bigger prism, I denote by m2. So here is the left end of this smaller prism. When it reaches the other position shown at the bottom, this horizontal distance will be equal to, I mean horizontal distance moved by the smaller prism relative to the bigger prism, means this distance. That will be observed. You can observe from here to here it is 5L. From here to here it is L. So 5L minus L. That will be 4L. So because the combination rests on a smooth horizontal floor, and the smaller from conservation of linear momentum, as explained in question number 34, the smaller prism shifts towards right in the horizontal direction. Then horizontally the bigger prism moves towards left side. Let S1 be the magnitude of the horizontal distance through which the smaller prism moves towards right side. Let S2 denote the magnitude of the horizontal displacement of the bigger prism which is directed toward left side, or the magnitude of the distance. This distance moved by the bigger prism to the left side, which you have to find. So magnitude of the relative displacement, because the two displacements are opposite, magnitude of the relative displacement of smaller prism with respect to the bigger prism will be S1 plus S2. That is equal to 4L here. As explained in the question number 34, repeating the procedure of the question number 34, you can write M1 S1 equal to M2 S2. So M1 is M here, M2 is 5M. So you get S1 equal to 5 into S2. Now you can substitute the value of S1 from first equation into the second equation. So you get 5S2 plus S2 equal to 4L, or 6S2 equal to 4L, or you can write S2 equal to 4L by 6, or 2L by 3. So S2 is the horizontal distance moved by the bigger prism to the left side with respect to stationary observer on the earth. So that is the answer. If you want to copy the solution of this problem, you can take a pause and copy the solution of the problem. So for the question number 52, which I just now discussed, third option will be the answer. That is 2L by 3. So next, look at the question number 53. A thin rod of length L is lying along x-axis with its ends at x equal to 0 and x equal to L. Linear density, mass per unit length, varies with x as k into x by L whole power n, where n can be 0 or any positive number. Position XCM, center of mass of the rod, is plotted against M. Which of the following graphs best approximate the dependence of XCM on M? So you can analyze the graph. If you consider the case where n equal to 0 and n equal to 1. So here mass per unit length, the linear density, I denoted by nu as I discussed one of the problems. That is given to be x by L power n. So let us consider the case when n is 1. Next coordinate center of mass, can consider the rod to be made up of large number of similar small elements, each of infinitesimally small thickness dx. For the left hand x is 0, the right hand x equal to L. So consider small, the rod can be imagined to be divided into large number of small elements, each of infinite small thickness dx. So by the method, we can follow the method I discussed earlier in one of the examples to find the position of center of mass for continuous bodies by the method of integration. XCM equal to integral x dm by integral dm between x equal to 0 to x equal to L. So let us find the value of xm in the general way. So here x mass of small element can be written as mass per unit length into length of the small element. We'll analyze the situation separately. First we'll derive it in the general way. So x into nu dx, nu you can write k into x by L or n. dm is the mass of small element of the rod with infinite small length dx. That is equal to mass per unit length into length dx. Mass per unit length you can write k into x by L whole power n. So that is x into k into x by L whole power n dx 0 to L divided by integral dm means integral of k into x by L power n dx from x equal to 0 to x equal. So k is a constant, you can put outside integral symbol both in numerator and denominator. So k into L power n into integral of x power n plus 1 dx 0 to L. The denominator also you can take k by L power n outside integral symbol because L and k are constants into integral of x power n dx 0 to L. So k by L power n gets cancelled. So integral of x power n dx you can write x power n plus 1 by n plus 1 0 to L. Same way numerator you can write x power n plus 1 by n plus 1 from 0 to L. So you get xcm equal to n plus 1 by n plus 2 L power, if you apply the limits, n plus 2 divided by L power n plus 1. Or you get xcm equal to n plus 1 by n plus 2 into L. So that is a general result. So if n is 0, you get xcm equal to L by 2. So if n equal to 1, you get xcm equal to 1 plus 1, 2. 2 by 3L. Like that. So if n is infinity, can you divide numerator denominator with n here? The last result you can write, again I am writing left side xcm equal to 1 plus 1 by n divided by 1 plus 2 by n into L. So when n is infinity, 1 by n becomes 0, 2 by n also becomes 0. Then xcm will be L. So you have to see where all these conditions tally out. That means in which one of the graphs you get n equal to 0, xcm equal to L by 2. Those who want to copy the solution of the problem, they can take a pause and copy the solution of the problem. So in which one of the graphs you have to check up, all these three conditions are fulfilled. Come on, look at the graph again. So you can look at the 4 graphs. You can observe that. So only in the third graph, you get on y-axis n is 0. That is, at n equal to 0, you will get axiom equal to Ly2. And for n equal to infinity, axiom equal to L. So the conditions, the results will tally with the third graph. So third option is the answer for this question. So I will be continuing the discussion of the remaining questions